tangent bundle. Now we go with the definition of the tangent bundle. And we will interpret it as a differentiable manifold. So what we can say, the tangent bundle is just the union of all the tangent spaces at any point of a given differentiable manifold M. Now there's a natural map called fibration, which goes from the tangent bundle to the base manifold. And this map acts like this. Q of V is equal to P if and only if V belongs to Pm. Now, in order to grasp what the tangent bundle actually looks like locally, we can actually say the following thing. The canonical vector basis xi of the tangent space to the point P of a manifold M are related to the curve P plus T EI, where EI is the canonical basis 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, etc. So they correspond to this. While if we go into the algebraic formulation, then this the canonical basis at the point P of a tangent space to a manifold M are given by the partial derivatives, are related to the partial derivatives via the coordinate maps. Now, if we pick up a given point, let's say we have an open set W of Rm. Now, if we pick up a point, a vector V in Rm, then to this vector we can relate the curve P plus Vt. These equivalence classes of curve tangent to point P are strictly related to the vector xv itself. So xv itself can be viewed as the equivalence classes of curve or curves P plus Vt. So what we have to do if we want to describe the tangent bundle to the open set W. W is an open set of reals. But we have just to pick up a point P of W and a vector V in Rm. So TW, tangent bundle, is actually equal to W product Rm, and is a subset of R to the 2m. Basically this. So now we know how a tangent bundle looks like locally on a given real Euclidean space. Now let's say that we have got a function f, a k-regular function f, from a given differentiable manifold M into Rm. We can construct the differential of this function. The differential is another map which goes from T M, the tangent bundle of M, into the tangent bundle of Rm. But we know that the tangent bundle of Rm is actually Rm times Rm. So we can, in some sense, construct what a coordinate homomorphism can be for the tangent bundle. So we have two natural projections. We have the projection on the first factor, which are actually the function f itself, and a projection on the second factor, which we call pi. So we can set small d of f at the point P equal to pi big D f of P. And the differential d of f at the point P computed in the vector on the vector V belonging to TPM is basically equal to the couple fp and small differential of f at the point p computed on v. Among all the regular function we can build, interesting are the real valued function of several variables, real valued. Now, how these functions are? We can build the differential of f, because f is a map which goes from M into the reals. For example, we can build the big differential dfp computed in V, but this is the couple, as we already said, fv, the projection on the first component, f of p, and small d of fp computed in V. But when we are interpreting the vectors of the tangent space to the manifold at the point P as derivations, then we have just that the small differential of f at the point P computed on V, or on x, in case we are denoting a derivation, is just equal to xf computed in P. Okay, so what we have? We have that the small differential of this kind of function, real valued function f, computed at the point P, are nonetheless that elements of the dual space of the tangent space at the point P of the manifold. They are useful because when we consider other kind of maps which are homomorphisms, in particular, if we consider, for example, a chart over M, so a couple U phi where U is an open set, then we can build the big differential of phi, and this is actually equal to the couple phi, small differential of phi. But the small differential of phi can be viewed when we restrict ourselves, and so we are just saying, okay, we have already introduced the coordinate chart, so we are free to use real variables at will. Well, this is actually equal to phi differential of x1, differential of x2, differential of xn. This means that when we pick up a point PV belonging to the tangent bundle TU, we obtain, as a result, via the map's big differential phi, we obtain elements of U times Rm. But U times Rm is a subset of R2m. So we obtain that the dimension, if we consider this capital D phi as the coordinate homomorphism for the, let's say, differentiable manifold tangent bundle, then we have that the dimension of the tangent bundle must be equal to twice the dimension of the base manifold M. But how can we build the differentiable structure of the tangent bundle? First of all, we need a topology. The topology we implement over the tangent bundle is nonetheless that the topology which makes this coordinate homomorphism d phi continuous. So let's consider, for example, a chart U phi, and assume that phi of U is equal W. Now consider a subset, an open subset of W times Rm. Let's call this B. Then we can construct the map d phi to the minus 1. But d to phi to the minus 1, when applied to B, gives actually B another set B phi contained inside the tangent bundle. And we require that these B phi are actually open sets. So, by varying B and by varying phi over the coordinate charts, we obtain a family of subsets of the tangent bundle, which we require to be open by definition, and which also we require that they form a basis for the topology of the tangent bundle. So we have obtained a topology on the tangent bundle, which is also trivially Hausdorff, and we have these maps d phi, which in turn act like coordinate homomorphisms. So the other ingredient we need is actually the change of coordinates. So let's pick up two coordinate charts for M. Let this be u phi and v psi. Now we can be obviously assume also that u intersecting v is no empty. Assume, for example, that d phi is a map from T of u intersecting v into w prime times Rm, and d psi goes from T u intersecting v inside w second times Rm. We can construct the map d psi composite d phi to the minus 1. A theorem says that this is actually equal to d phi times psi to d psi times phi to the minus 1, and this is a couple psi composite phi to the minus 1 and the small differential of psi times phi to the minus 1. Okay, but d psi times composite phi to the minus 1 is actually the Jacobian of the map. So we obtain as a result that those maps are obviously ck minus 1 regular. So the tangent bundle is a ck minus 1 differentiable manifold when we implement it via the coordinate charts obtained with this small d, with this big D phi, and the open sets we have already discussed. So it's a manifold of class k minus 1 if the basis manifold is of class k. This is first thing. Now let's speak about the sections of the tangent bundle. Tangent bundle has got section, but what is a section? Let's consider a k-regular function f from M to N, where M and N are two differentiable manifolds. We say that G from N to M is a differentiable section of F, just in case G composite F is equal to identity of M. In this way, given the tangent bundle Tm of a differentiable manifold M and the vibration Q Tm into M, a vector field is by definition a differentiable section of the vibration Q. Furthermore, if we have a submanifold Y of M and Q to the minus 1 of Y is a vector field, then it is a section of the vibration Q tie Ym into Y. So every section of the vibration is a vector field. Every vector field is a section of the vibration. We have this by definition. Now, consider an open set U in Rm. Now, how vector fields looks like on Rm? They are just a summation of a x1 xm derivative with respect to x1 plus blah 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 blah. So they are of this form. So they are actually maps V from ck into ck minus 1. So real function of class k into real valued function of class k minus 1, which satisfies we satisfy the Leibniz rule, in the sense that VFG is equal to VFG plus FVG. Now, it's step forward that in case the coefficients of the, let's call this the coefficients, are smooth, then the vector field is a smooth vector field and is a first order differential operator, so over the space C infinity. Furthermore, if we restrict smooth vector field to a given point P of the manifold, we obtain a derivation. We obtain easily a derivation, so an element of the tangent space to the manifold at the point P. Obviously, the sum of two vector fields is a vector field, and the product of a smooth function for a vector field, smooth vector field, is also a smooth vector field. We call K infinity the set of all smooth vector fields. On this space of smooth vector fields, we can introduce a bracket, so a map, bilinear map, with respect to the reals, from K infinity into K infinity, which satisfies three properties. The antilinear properties are obviously bracket x y bracket is actually equal to xy minus yx. As I was saying, this bracket satisfy three properties: the antilinear property, antisymmetric property, so bracket xy is equal to minus bracket yx, the Jacobi identity, and a sort of derivation which is actually fxg is equal to f bracket xg xy minus yfx. Okay. Now consider an algebra. An algebra is a set where is introduced a map of the type product. For example, AB, A is an algebra, so there's a map point, let's say product, which goes from A into A. And now there are different algebras if we consider properties, additive properties, or further properties for this product. But what we just need is that definition of derivation. A derivation over an algebra is a map from A into A, such that DAB is equal to DAB plus B plus A dB. Okay, this is a derivation. Now, a theorem says that a vector field is a derivation of the algebra C infinity of smooth function, real valued smooth functions. And every derivation of the real valued smooth function space can be implemented by a vector field. Okay, now we want to introduce what is the implicit function theorem and also the inverse function theorem. They are very important in the context of submanifolds and in general to obtain solution to equations and whatever. So let's first state the statement of the inverse function theorem. So let U be a subset of R M, subset of R M, open subset of R M, and let F from U to R M be a CK function, so a K regular function. Assume let P be a point of view. Let P be a point of view and assume that the differential, small differential of f at the point P is invertible. Then there exists a neighborhood W of P contained in U such that f of W is open in Rn, and f, when restricted to W, is a diffeomorphism of class Ck on the image. This is the inverse function theorem. Now, we say that a function f between two manifolds M and N, a function f of class Ck, is a local diffeomorphism. If for any p belonging to M there exists a neighborhood W of P such that f of W is open in Rm, and f of from U to Rm is a diffeomorphism. So it's a local diffeomorphism if those properties are satisfied. In this way, the inverse function theorem can be stated also for manifolds. Let f be a k-regular function from two manifolds, from a manifold M into a manifold N, and assume that f is a local diffeomorphism. Then the big differential of f at the point P is a map from Tpm into Tfpn, and it is bijective. Now let's go to the implicit function theorem. There are two versions of the implicit function theorem. The first one is the surjective version. The second one is the bijective. Is the injective. So let's state first the surjective version. Consider a point P over M and an open neighborhood U of P. Assume that f is a function from U to Rn. So it's a map from Rm to Rn. Assume also that fp is equal to 0 and the differential of f at the point P is a surjective map. Then there exists a neighborhood W of P contained in U and a local diffeomorphism phi from W to Rm such that f of phi x1 xm is equal to x1 xn. Surjective version. The injective version is the following. Suppose P is a point in Rm and U an open neighborhood of P. Let f be a map from the open U inside Rm. Assume also that pick up a point. Assume also that f of P is equal Q, with Q belong to M, Q belonging to N, and assume that the differential of f at the point P is actually injective. Then there exists a neighborhood W of P contained in U and the local diffeomorphism phi such that phi of there's an open neighborhood W of Q and the local diffeomorphism phi such that phi of Q is equal to 0 and phi goes from W into Rn such that phi of f of x1 xm is equal to x1 xm 0 0 0 0 0. This is the implicit function theorem. Now we want to relate the implicit function theorem to the existence of submanifolds for a given differentiable manifold M. How can we relate these things? First of all, let's consider a k-regular function f from a manifold M of dimension small m into a manifold capital N of dimension small n, k-regular. Now, by definition, a point P of M is called a regular point of F just in case the big differential of F computed in P is surjective. If it's not surjective, the P will be called a critical point. Furthermore, a point Q belonging to N is called a regular value of F if any P belonging to F to the minus 1 of Q is a regular point. This is definition. A theorem holds, and the theorem says this. Assume f is a k-regular function between m and n of dimension respectively small m and small n. Assume that q belonging to n is a regular value, or let's say, assume that 0 belonging to n is a regular no. Assume U is in Rm. Assume U be a subset of Rm. Assume U be a subset of Rm, and f a function from U to Rn being a k-regular function. Assume that 0 belongs to n, and such that 0 is a regular value of f. Then we have that f to the minus 1 of 0 is a submanifold of M of dimension small m minus small n. Now we give another definition, that of transverse manifold with respect to a given function. So let f be a k-regular map from a manifold M into a manifold N. We say that a submanifold A of N is transverse to F just in case for each Q equal F of P, such that for each P belonging to M's and Q equal Fp belonging to A, one has that T N Q is equal to the image via the differential of F at the point P of TPM plus TQA, transverse. Now a theorem holds, and is the following. Suppose that f from M to N, suppose that f from M to N is a k-regular function between a manifold M of dimension small m and a manifold N of dimension small n. Assume that A is a submanifold of N of dimension small a. In case A is transverse with respect to F, we set zeta A equal F minus 1 of A, and in case zeta A is also not empty, then zeta A is a submanifold of M of dimension small m minus small n plus small a. Furthermore, if Q is a regular value of the function f, then f minus 1 of Q is a submanifold of M of dimension small m minus small n.